So we got to the point where we designed the amplifier and we'd determined that the voltage gain was going to be 10, which was proportional to R minus RC over RE. So we also determined that Z in was greater than the 10k, because we said it was around 17.5k, so that was all good. Quiescent current flowing here we calculated as 1 milliamp, so ICQ was satisfied because that was 2 milliamps. The only thing that we failed on was the output impedance, and this equated to 5k, and it needed to be less than 150 ohms. So what could we do? Well, we could start redesigning the whole thing, and we could say, well, let's make RC 100 ohms, therefore giving us the Z out straight away being less than 150 ohms. That would have an impact, however, on the quiescent current. We're going to see this rise up to 50 milliamps plus. And that's also going to mean that we're going to have to, in order to maintain the gain, we're going to have to reduce this to around 10 ohms, which then will affect the input impedance, and everything gets messed up. So I would encourage you to try that, work through these design equations and see if you can satisfy this with a much smaller RC value. What I'm going to show you now is a different approach, and one that's adopted usually in design, where we design in stages. So this becomes our voltage gain stage, and what we're going to pop on here is a current gain stage to lower the impedance, or lower the impedance at the output and increase the drive capability. So what we're going to do is just extend this. So this is going to be the input into a what we call a voltage follower. So here we go, and poof, it's as simple as that. Now this we will call RE2, and this we will call RE2, little RE2. What can we say now about this output impedance? Well, the output impedance, if we looked at an AC model of this, would say that the output impedance, or the impedance looking in, is the RE2 and RE2, the little RE2, in parallel with the source impedance, so the output impedance of this amplifier. And if we draw out the equation for that, Z out equals, and so we have RE2, and this is in parallel with little RE2 plus the source, which in this case is the RC divided by beta plus 1. So there we have the overall design equation for the output impedance of this system. So what we need to do is think about what the voltage is going to be across this, or DC voltage is going to be across this RE2. Well, we can calculate that because we know that there's going to be a volt drop here, approximately 0.65. We've DC biased this to be at 5 volts, so we can predict that this is going to be approximately 4.35 volts. What we can then do is choose an arbitrary value of RE2, so we can then see what the quiescent current, i.e. 2Q, is going to be, if you like, through there. So let's just choose a value. Let's call this 270 ohms, say. So if we say that's 270 ohms, so that's RE2 equals 270 ohms as a starting point, we can therefore calculate that IE 2Q is going to approximate to 15.8 milliamps. Okay. So Then what we can say is we can calculate the value of RE2, because RE2 is 26 millivolts divided by this 15.8.9 milliamp value, 8.8. Therefore that's going to be 1.63. So we know that RE2, we've calculated RE2, we know that that's going to be 201, we know that that's going to be 5K, 1.63. RE2 we've chosen to be 270 ohms, and therefore if we plug everything in to these equations, we're going to get a Z out of around 24.14 ohms, which is pretty damn good. We've satisfied that equation. Now we can see that the IEQ, because this is constantly biased, is gonna well exceed our specifications in terms of quiescent draw as a system as a whole. However, what we've demonstrated is we can break the system up into stages, if you like. Now the ideal solution would be to design probably a class A voltage stage and then put it through a push-pull amp, so it becomes class AB. And by doing so, what we do is we put two transistors in series, if you like. One is going to switch on during this phase and the other is going to switch on during this phase. Obviously we'll get crossover distortion, but we can we can mitigate that with a few other design tricks. But this hopefully demonstrates that we can without changing this stage in any shape or form, we can add a voltage follower which can then make our amplifier drive much smaller loads. We could modify this even further. We could increase or reduce RE2. We probably, by increasing it, we're going to relax and therefore decrease this quiescent draw even more. So again, play around with the equations and see what you can come up with.